Hey there everyone. This video will be deriving the expression for the moment of inertia of a solid cylinder. Okay. Again, like the previous video on a rigid rod, this video is completely optional, right? I won't require you to know how to do this for an exam or anything. It's purely for your own edification, okay? You don't have to watch this if you don't want to. But if you do, feel free to continue watching. So, the first point, or the first thing to do, would be to draw a picture. So here's kind of my cylinder, something like that. All right, and this will be for when the cylinder rotates about the central axis. So the axis is going through the center long ways, like that. The cylinder is of length L and radius capital R, all right? And I guess also of mass M, capital M, if you will. All right, so the goal is to most easily split this up such that we can integrate all of the masses over the entire object, right? Because the moment of inertia expression is integral r squared dm, which means the r squared, right? The distance that each differential mass is from the axis. We want to integrate all of those, and thus we'll get the total expression for I. And so the easiest way to do that, or one of the easiest ways, is to think of symmetry. Okay, how can we break this object up symmetrically to make our lives easiest? Well, we want to ultimately get all of this volume, right? All of it. Well, if you think of a cylinder as simply a bunch of circles, or rather discs, right? A bunch of solid discs stacked on top of one another, they're basically of infinitely small thickness, but if you have an infinite number of them, well, a bunch of discs added up to length L, that gives you a volume of the cylinder. I should point out that the mass density is uniform. And so we call that Greek letter rho. RHO. That's the mass density. And that's equal to mass per volume. Okay, and so the volume of a cylinder is, well, I should have done it over here. The volume for a cylinder is, well, length times area, right? And that's area of each of those discs, each of the face. Well, that's just pi r squared, right? So let's see here. In our expression for I, we don't need just mass. We need dm, differential mass. So let me solve this for m. Gives us rho L A. Now, taking the derivative of both sides, we can see what we get. Well, the mass density rho, by definition in this case, that remains constant. So that doesn't change. The total length of the cylinder, that doesn't change. But what will change is the area. Why? Well, let's think here. Concentric about this axis, we're going to have a bunch of circles, all right? A bunch of discs of varying radii and varying area. So we're going to take all of these circles and add them up at bigger and bigger radii until we get to the entire thing. Okay? More specifically, we're going to have this. So we're going to have, let me draw it like this. We're going to have a bunch of circles, but they will all be length L. Right? They will all be of length L. So we'll just expand the radius until we get to the maximum radius, capital R. And so this is of radius lowercase r. Thus, the dA is the area right there. And that's what's changing. So we want to take this expression here and plug it in right there. And so this is what we get. We have r squared, and our dm expression is now rho L dA. Okay, I guess I don't need parentheses there. Okay. Aha, now, what is our area? Well, I'll pull out the rho, I'll pull out the L, leave R in the integral, and now differential area, well, area of a circle is simply pi r squared, right? Then that means dA is the derivative of that, 2 pi r dr. What's that? That's pretty much the circumference times the radius. So that means we have 2 pi r dr. And now we're integrating with respect to just radius, whereas we used to be integrating with respect to A and mass, right? But we can do this now. So rho, let's do this. I like the pi's at the very front. 2 pi rho times L times integral of what we have now is r cubed dr. And our limits, well, we're going from the central axis of radius 0 out to a maximum radius of capital R. So let's see what we get. 2 pi rho L, let's see, that's r to the 4th over 4, which gives us capital R to the 4th over 4 minus 0. All right? And keep evaluating this. We have 2 pi, well, let's plug in for rho, actually. Rho is equal to mass m divided by volume. If you remember, volume is simply the length of it times the area of the cylinder, which is pi capital R squared, times our L times r to the 4th over 4. All right, so pi goes away. This term of L goes away. 2 factors of r go away, so that's a 2 now. And this 2 cancels out this 4, gives us 2. So we have m r squared all over 2, and that should match the expression in your moment of inertia table. 1/2 m r squared. And this is the moment of inertia expression for a solid cylinder rotating about the central axis. Okay, that's it. Thanks for watching.